Good afternoon, everyone. Welcome to our pre-lab lecture. Hope so far so good in terms of the previous labs. Before we get started, if you can see on the chat feature, chat box on the Zoom conference, I requested you to have a paper and a pen so that you can take notes. I went through the lab procedure. I went through the data sheet and the calculation in these labs. The calculation in particular in this lab is intensive and it requires some of the concept equations you may have forgotten going all the way to Chem 1, and that's why I say please have a pen and a paper so that you write the notes. I'll try as much as I can from where I am to give you equations you will need. So if you don't have, if you don't write them down, chances are you will find it difficult completing the data sheet and the calculation. So I expect you to take notes, ask questions using the chat box, and I'll stop. So for now, let me just share my screen and I will walk you through what we are going to be doing in determining the kinetics of glitching action using a smartphone. Let me just share my screen. All right, I'm gonna share my screen and see if you can write down notes on each and every item on the data sheet. Let me share my screen. Right now, you should be able to see the data sheet and the lab procedure. This is the lab procedure, and this is the data sheet. This is the data sheet. I have my whiteboard here. Let me just minimize this, and I'll be writing the notes or giving you the equations you will need for completing the data sheet. And please show your calculation, your work. I always put on the rubric how you will be graded on each lab report. There is a chat box here. Please use the chat box in case you want to ask question. All right. I'll keep an eye on who is joining us during the course of the lecture. So at the outset, I hope you have downloaded the calorimeter on your smartphone. All right. The calorimeter should be able to detect the blue color, the green color, and the red color. You should also have a background, excuse me, you should have a red background or something similar to this. That is where what is being mentioned in the data sheet, that you should have a red background you're gonna place on your table. And of course you can use the stopwatch on your phone, or maybe you can request somebody in your household to help you with their smartphone, or if you have a kitchen timer, you can use that to time the reaction. You should have purified water. If you don't have, please do not use tap water. Might not work because the solution will be clouded. It shouldn't be clouded. Therefore, preferably distilled water from the Walmart. That's what you will need. And at some point, you will make a water bath. That's why it's called for a stove, or maybe electric kettle, so long as you have what? You have the ability to make a water bath. OxyClean, this is the only This is what you're gonna be using to determine the bleaching action. It's just the peroxide. We'll see the peroxide later on when we do the calculation. These are the assorted food with their dye. So just print this, take with you when you go to the store. If you don't have the material right now, if I were you, I will print out this so that I'll get the right material which will work. The objective of this is to determine the rate law, all right, to determine the rate law of a chemical reaction. And remember the rate law from the previous experiment. Rate law is given by this, or it will look like this. In our case, by the end of this lab, you'll write a rate law with the rate constant times the concentration of the blue one dye, all right, raised to some exponent, which is the reaction order with respect to blue dye, and times the concentration of, times the concentration of peroxide raised to some value we call the reaction order with respect to peroxide. This is the objective of this lab, all right? If we know the rate constant, if we know the concentration of the blue dye, the reaction order with respect to blue dye or blue one dye, all right? And the concentration of peroxide raised to its respective order. We will collect the data. We will determine the rate constant, all right? We will determine the reaction order with respect to blue dye. We will determine the reaction order with respect to peroxide and the concentration of each one of them in order to do it, in order to write the rate law, okay? Write the rate law. And then we will determine the activation energy using the Arrhenius equation. Remember Arrhenius equation? If you are taking the course right now, you should have come across, or you should know this equation. I guarantee you will make use of this equation in either the quiz or exam. You take, or it is in this form, ln of K1, K2 over K1 equals to negative activation energy over the rate constant times the reciprocal of temperature 2 minus the reciprocal of temperature 1. This is called Arrhenius equation. And using this equation, we can determine the activation energy using the algebra, rearranging the equation. Activation energy EA equals to negative R times, maybe I should have write that times here, times ln of K1, no, K2 over K1 divided by 1 over T2 minus 1 over T1. This is the equation you will need to determine the activation energy. Look at this equation right here. What I did is just, take the negative on that side, sorry about that. If you look at the negative, there is a negative on activation energy. I'll just take with the negative R to end up with a positive activation energy, and then I divide the whole of this. The whole of this will be my my denominator. On the other side, I'll take the R, maybe I'll just erase that and have the negative with the R. And this is the equation. This is the equation for determining the activation energy. Those are the two things you will need, all right? Those are the two things you will have to, at the end of the lab, you should be able to calculate activation energy. That's the last thing we will see. All right, in between there are a lot of calculations. Some of them you don't even have the equation in the background. And I'm not going to read each and every paragraph, each and every section in the background, but I just want to dive into the data sheet and how you will collect the data, which equation you are going to use for part 1, for part 2, and part 3. All right. So you're gonna need the equations for part 1, part 2, and part 3. All right. This is the equation. If you look at, if you have the, all right, if you have the data sheet, or I mean the handout with you, this is the rate law we are going to determine by end of the experiment. Look at this. This is what we are going to try to rate law, all right, is equals to directly proportional to the rate constant times blue die 1. This is what we are trying to achieve. And I know last time we use method of initial rate, even though method of initial rate is used in between here, we are going to use the graphical method to determine, all right, the graphical method to determine the rate law or pseudo method, all right. Pseudo method, if you read in the pre-lab, there was a question about 2 methods. In graphical method, all right, in graphical method, I know I explained to you graphical method determination of reaction order, that how are you going to determine that? There is the 0 order, all right, there is the 0 order, there is the first order, and there is the second order. How will you know that it is first order, it is second order, it is first order? It's by understanding and mastering the plots of concentration on y-axis versus time on x-axis. So you're gonna generate graphs in order to say first order, in order to say second order, or say first order. You have to graph on y-axis the concentration. Remember, this means concentration. This means concentration. You should know this. I know you are familiar with the bracket. It means concentration. So if we have concentration of A, we will represent a star. If you see, this is concentration of peroxide, concentration of peroxide. Colorimeter, you know, we're just gonna be looking at the changes in observance or the color transmitted. And based on the color or the intensity of the color, we will relate the concentration with the observance on the colorimeter using the Pierre's law, which is also something you may have learned before. Observance, or sometimes this is APS for observance, or in our case, it will just be A for observance. Understand what that means. This is observance. And we will relate the concentration with the observance in the sense that from the Pierre's law, A, which is observance, is directly proportional to epsilon naught or molar absorptivity times the path length of the cuvette. The cuvette is the, you know, the cell, sometimes it's called the cell, times the concentration. This is concentration, and it is what? It is just molarity, which is the concentration we are just referring to in our case here. If you look on the data sheet, on the y-axis right here, we have the concentration. So if I were you, forget about the concentration on this diagram. It's just gonna be observance versus, all right? It's gonna be observance on this side, A, versus time on this on x-axis, the time it takes for the reaction to go to completion instead of concentration. So if you have a negative slope of a graph where you have the observance values on y-axis, then you make a conclusion that it is a zero order. If you have a negative slope, you know, it just looks exactly the same, all right? But the difference is what is on y-axis. If it is the natural log of the concentration of, or in this case, ln of, it's gonna be ln of A, which is the observance, not concentration, observance on this side, and then we make a conclusion as first order. Reciprocal of concentration of A with time, if you have a positive slope, and then you know that it is second order. This is the graphical determination of reaction order for a reagent, okay? So there is a method of initial rate we used last time. We're gonna use it today. And today I introduce you to graphical method of determination of the rate order. So you suspect that if it is zero order, let me plot this on y-axis versus time. Is graph looking like this? If it is not linear, and then it is not zero order. Nowhere will you end up with three of them being positive or two of them being positive. One of them should test positive for the reaction order, So that's one thing I want you to know, understand the graphical method versus the method of initial rate. Let's see part one. How are you going to proceed? What does part one say? I don't want to just go through each and every statement in there. Let's just dive into the procedure and see what we are going to do. If you look at the data sheet and the procedure, you gotta use a graduated cylinder. I know you do have that. And I'll recommend maybe 7 grams of OxyClean. OxyClean, should use OxyClean, which is the same as sodium percarbonate. The chemical formula is right here. Look at the data sheet below. That is the chemical formula for OxyClean. And there is the peroxide in the chemical formula. All right. Remember to use the distilled water. Please, when you are working for this to work, make sure that you don't have foam. You know, it might form. Be gentle. You should stir gently. So if you look at what the direction calling for here in step 2, write exactly the grams of OxyClean you're gonna be using. And there is the stock solution. You know what stock solution means? That means what you will be using throughout the experiment, stock solution. If you recall how you used to go get the reagent from the fume hood, those were stock solution, okay? That is what you will be using throughout the experiment. You are preparing the stock solution in part 1. Now, how do we calculate the total volume of the stock solution? If you measure out 50, all right, you will see additional 50. So you should have a total of what? A solution of 100 ml. So you should have 100 ml of stock solution. This is what we'll be using throughout the experiment. You have to calculate the concentration of peroxide in the stock solution. because that's what's going to be our focus. Remember our rate low peroxide is in there. You have to be knowledgeable on the stoichiometry. If you look at the peroxide, depending on how many grams of oxyclean you have, there is 0.5 moles for every 1 mole of oxyclean. You have 1.5 moles of peroxide. You have to multiply by 1.5. So if I know the moles of oxyclean, the number of moles of peroxide will be 1.5. You see, 1.5 moles of peroxide per mole of percarbonate. So if you know the grams, say if you measure out 7 grams of oxyclean, you have to find how many moles using the molar mass of oxyclean. You know the number of moles of what? Number of moles of oxyclean. The number of moles of peroxide now will be 1.5 the number of moles of percarbonate. That's what you need to remember. So I'll multiply by 1.5 to do that. Now, once you get the number of moles of peroxide, you will calculate the concentration of peroxide is given by the number of moles of peroxide, all right, H2, O2, like that, over volume in liters. You know how to find the concentration. Remember, this is the volume of stock solution. That's the volume of stock solution. And that will give you the concentration of peroxide. Look at the data sheet. That is what you need to do in terms of determination of concentration or molarity of hydroxide. Any question? Any question? Somebody say yes on the chat feature, please. Are we all on the same page? We have a long way to go. Are we all on the same page? Yes, thank you, Nicole. Thank you, thank you, thank you. Yes, so that is what you need. If you look at, you know, you have to remember. So if I know, let me just pick up the hypothetical concentration of 0.2. 0 molar. I just pick up this. I'm just picking up this for the sake of calculation, because down the line we'll be required to do that. So let's move on to the next section on how do you determine the concentration. If you once you obtain that, you know, they will call for, you're gonna need something similar to this. Is to call about the rate. Okay. Please change these to obtain a clean 250 ml picker. If you look at the picker given in your lab, all right, it's somehow not clear. You know, when I look at the, you know, when we made this with my colleagues, we didn't know that the picker will be cloudy, kind of like, you know, you have seen that even the graduated cylinder is not really clear. It's not transparent the way you know, you're familiar from the lab, that it is glass. You can easily read the calibration. Since, all right, since you want the color to, you know, the red to come through the solution, I'll recommend use the plastic transparent cups instead of the bigger plastic transparent cup which came with the lab kit. That will work, because when you place on a red paper or red background, you should be able to see through. Otherwise, with the picker being recommended here, it will be like white there. You wouldn't be able to see the red background, especially when you prepare a solution of percarbonate, it will be so cloudy and the calorimeter will not work. So take note of that, that everywhere where it's talking about a picker, you may say, oh, the direction is saying, use 250 picker, and it didn't work. I didn't see any value. I was trying to do the calculation. It's because, I had to do it myself to make sure that it is working before you guys, do. And that's why I'm pointing out, I mentioned that there was some correctional method. Everywhere you see 250 ml picker, just use the regular cup and prepare your solution. Okay. Now you'll now do what? You will prepare using 50 ml picker. You'll measure out 80 ml of DI water. Of course, the graduated cylinder has a capacity of 50 ml, 50 fast, and then what? And then started to make it 80, and then you transfer it into your prepared solution, which is you see this 50 ml transferred into a beaker, which means you're gonna transfer it right here. Remember, you had your stock solution somewhere. You had your stock solution. This has nothing. This is just water. Now, look at step number 9. It doesn't mention anything, but there's something which you will, or some of you will be like, oh, I couldn't have figured it out that. Step number 9 is you have to measure out your, 20 ml of your stock solution, and you know this concentration. You know the concentration of your stock solution. So if I measure out the 20 ml, you will add, look, calculate the dilated, so if you measure out 20 ml into the water, what is the ml of water? 80 plus 30 is 100 plus 20. So total volume here is, total volume after number 9 is 100 ml, 100 ml. To calculate the concentration, look at step number 9. To calculate the concentration of peroxide, say dilute. There is the dilution law. And I know some of you forgot, right? You wouldn't have really figured it out. I know we used a different equation before, but number 9, you got to use this M1, V1 equals to M2, V2, all right? This is V2. You diluted the volume to 100 ml. V1 is you took 20.0 ml of the stock solution. The concentration of stock solution, remember I picked hypothetical value of 0.2. Don't say that, how did I end up? This was hypothetical value, hypothetical concentration of peroxide. So you're gonna use dilution law to find the concentration you are looking for, this, of which this implies M2 of V2 equals to what? Equals to, no. What I want to, or what I meant to say is M2 is given by M1 V1 of V2, and you know the values. For step number 9, I know you're like, oh, I wouldn't have figured it out that. I wouldn't have figured it out that. That is what you need to do to find the concentration of the peroxide, concentration of the peroxide in your solution. So that's what you need for step number 1. We're gonna be using again, the M1 V1, all right? We will be using the M1 V1. That's the concentration. Write that somewhere. The initial temperature, you gotta measure using the thermometer and record in the data sheet. For part 3, step number 10, you see it's being mentioned like step number 3. If you didn't take a chance to look at the data table, this is part what? This is part 2. But in part 3, where you're going to record the temperature, this is part for part 2. Record these temperatures in part 3. You see here? This is room temperature and salt. So I'll record here the initial temperature. There is the final temperature. What is initial? And I know you know when you say initial and final, they want you to record the temperature before you start the reaction and after the reaction. That is the final. So I want you to pay attention that when they say that measure the initial temperature of sodium bicarbonate solution, again, after the reaction, that means your final temperature, and then the initial temperature is before you add the peroxide into before you add the food dye or blue one dye into the peroxide. So we measure the temperature, record it in there. Obtain the red piece of construction paper, that's what I wanted to use, and then place over the sodium bicarbonate, place the solution. So if this is solution, you're just gonna place in there, and you will record, or at this point you should be ready to do it, to perform the experiment. Pay attention to the red color number. So this is the cell phone, and this is above. You're looking from above, and the purpose is it should be transparent, like you can see the red in there. Okay? If you use the graduated cell, the bigger the 250, it will not work. It will not work. So there is an illustration here. Red equals to 37. You will need to record the values for the red color. We call that initial. We haven't added anything yet. There shouldn't be any form on the surface, otherwise the experiment will not work. The experiment will not work. So nothing on my, say, if I have my bicarbonate solution, I haven't added any food or blue one dye in here with my smartphone. This is my smartphone here. You know, you will record 3 values. The direction code for, you know, taking a snap, you know, snap picture or snapshot 3 times to get the average value. When they say here, average 3 readings, you're gonna be doing 3 readings. This value here will not go anywhere in the data sheet, but you should keep it somewhere and label it. So if I take a snapshot, 3 paste average close, it will be 1, 2, 3. Average equals to 1 plus 2 plus 3 over what? Over 2 over 3 equals to, this will be my RO value, RO value, which means the blank. We call it blank. Nothing in there is blank. That value will not go anywhere. Please, when you do the calculation, label it as R subscript O for blank. You should be ready now with your stopwatch before you add the what? Before you add the red food additive on your solution. So you will initiate the reaction by adding a single drop of blue dye. So you prepare that based on the direction, okay? And gently. You'll prepare the food additive, and then you add what? You add the you add into. With your stopwatch, you'll initiate the reaction by adding a single drop of food coloring, that is blue food dye, and start the timer. If someone is around your household, please request them to help you with the stopwatch, okay? And you know, that way the experiment will run smoothly. Now here, once you add the drop, it might be in the service. It might just, the drop might be in the service. The direction called for starting, kind of like make it homogeneous. Make it homogeneous, all right, without creating the bubble. The reaction will go on, all right? The reaction will go on. You will start recording the data after every 60 what? After every 60, after every what? 15 what? After every 15 seconds. After every 15 seconds, you record the what? The data. Well, it is not a one-time, this is not a one-time data recording right here. If you look at 30, for example, let me say after 30 seconds, they want you to take the 3. Remember in the plank, we had to record the 3. Instead of recording, you will take a snapshot of maybe 4 and say 1, 2, 3, maybe 4. Let's say 3, let's work with 3, all right? So after 30 seconds, I'll be like 1, 2, 3. So this is the raw data right here. You wait for 45, after 45 seconds, 1, 2, 3, or 4. 1, 2, 3, 4. 1, 2, 3, 4. So you should have at least 3 snapshots for every what? For every data point. For every data point, that means 45 seconds, 1, 2, 3. After every second, so that you find the average. If you look at the data sheet here, you'll have to find the average. This is the raw data. Raw data is value 1, value 2. You don't need to do it while the experiment is running on. That is later on. You will come back to or go to your camera and then go back and find the average right here. This will be your R value. That will be your average. R, not R subscript, is given by 1 plus 2 plus 3. Those are the snap values for picture 1, for picture 2, for picture 3. And remember, this is for the red. This is for the red value. And then divided by 3. You will fill in right here. You will fill in for what? For the average red color value. Not red, the subscript was only for what? For the initial, with no experiment running in there. You will calculate for this column right here, calculated observance on the data sheet. Observance is given by R over R naught. R over R naught. That's how to find the observance values. Look at this. This is the equation. It's there is a negative. Sorry about that. It should be negative log of R, which is for each data point, that is 30 seconds, 45 seconds, and so forth. You will put it what? You will put it R over R naught. This is the blank value. This is the blank value, which you'll only run once. You'll only run once. And the top part here is for each what? For each run. That is what you need to do for part 1. I mean to say part 1. It's for 60 seconds. So that it's the same thing. For part 1 is this is the same thing. I went to part 3. It should be 60 seconds. You start right 60 minutes, 60 seconds, sorry. For part 1, it's the same thing. I use part 3. So after 1 minute, you record the file the same way. After 30 seconds, you go in there. This is for part 1, room temperature. You find the average. When they say average value for red color, it is the 3 values you will collect here. You don't need to collect right away, but take a picture of it. 1, 2, 3. Okay. If somebody is there to help you out, 1, 2, 3. Remember the calorimeter is above the transparent cup, not the beaker. Then observance, you use this equation. So far, so good? Yes, so far, so good? All right, Jacob, thank you. Now, here, you will find the natural log of the calculated observance. And then you will find the reciprocal of what? The reciprocal of observance, that is 1 over. You can use the spreadsheet, I mean the Excel to do that. And where we are going with this is to find the, here to find using the graphical method along with the appropriate time versus observance, you will plot the graph and determine the reaction order. Determine the plot type which gives you a straight line. R value, this is called the correlation factor. The correlation value, the closer to 1, give you that. One of them will test positive. For step number 18 there, they want you to find which one will give you a straight line. Is it this one? Ln of A, that is observance, not concentration. These should be observance values. Ln of A, not concentration of A, observance values. Will it give you a straight line like that, or will it give you for first order? Let me just zoom and see. Since we are only looking for 2 things, I think it is only, no, you're not gonna do the 3 tests. If I look here, they want you to plot a graph of ln of observance values. If ln is on y-axis and time on x-axis, and I see a straight line, and then I'll say that it is first order. The reason why you have the reciprocal of observance is so that you have ln on y-axis and time here, and if you get a graph like that, then you know it is second order. That's how to use the graphical method to determine the order. So if this is ln of A of time on this side, and then you know it is fast, all right? Fast order, that's how you use the graph. If I have 1 over A, which is the last column you see right here, on y-axis versus time here, and please indicate the units, label the graph, title. Don't just assume that the instructor knows what is going on. Have the title of the graph, label the y-axis, label the x-axis, and add equation of a straight line. All right, if you test, see which one is positive. If this is the case, like that, and then you know it is second order with respect to that. That is what you need to do in part one for determination of reaction order with respect to blue 1 dye. They call this blue 1 dye. All right, it is part of the reagent in our rate law. So once we know the order, we have ourselves what? We have ourselves this. This is where we are going. Remember, don't lose track. Don't get lost on the way. Remember where we are going in our equation is right here. We know at this point, we know, or we will have determined that. Let me use a check mark. Using the graph, we should know the reaction order with respect to blue dye 1. Blue dye 1. Any question on part One, how to find the reaction order. We have used the graphical method to determine the reaction order with respect to blue dye. Any question on part one, or we move on to part two? Can we move on to part two? Angelina Haho, can we move on? Angelina, are you there? Is everybody with me? Thank you. All right. Yeah. So nobody was responding, and I was like, "Oh, what's going on here?" So let's move on, class, to part two. All right, part two, you will have to use again the cup. You're gonna use the transparent cup instead of the 250 ml picker right here. It will not work. Trust me. If you use 250 ml, it's so opaque. Just in the same way we did, you'll obtain purified water, 80 ml, just the way we did before, 50 and 30, if you add, and then take again 20 ml of the stock solution from part one. Remember, we prepared the stock solution. You will measure out 20 ml. You measure 20 ml in the first part, so you should be remaining with 80. Now you go back again and take 20, remain with 60. Calculate the molarity of peroxide. So here again, you're gonna use the, we are going to part two. You will use the, M1V1 to calculate the molarity, all right? You will use the M1V1. Look here, calculate the approximate molarity of peroxide in the present dilution. How will you calculate that? It is by using M1V1. M1V1 equals to what? M1V1 equals to M2 V2. That's what you need for line 4 in part 2, line 4 in part 2, using the dilution law. Here, look at the data sheet right here. I sorry to be jumping around. The data sheet and the procedure, they are not one in one. But let's walk through the using the data sheet. Let's go to, in order to do the grams of mass of 1 drop of dye here in part 2, use step number 9. Look at for mass of 1 drop of dye, see step 9, number 9, on page 9, If you look at step 9, let's see step 9. In order to complete this right here, look at step 9. Determine the concentration of blue dye in each of these. In order to do that, first determine the mass of 1 drop of blue dye. You see here saying mass of 1 drop of blue dye. How are you going to do that? I know you have the balance. Tear out. I know you know what means tear out. So you're gonna use mass of 1 or anything you can have readily available and add 1 drop. So I'll tear this and add 1 drop. Record that as mass of 1 drop of the dye. Upon preparing your dye solution, you will have to use anything to measure the mass of 1 drop, which will come down here. The concentration of the blue dye in 100 ml, all right? Calculation of the blue dye. Remember, concentration of blue dye, let me just to save time, is given by the number of moles of the volume in liters. It is talking about in what? In 100 ml reaction mixture. If you are adding one drop equals to 0.05 ml, which is equal to 0.00005. 1, 2, 3, yes, liters. So if I'm starting with 100 ml of the stock solution, all right, you prepare the solution and you know the concentration of peroxide in there. Total volume will be 100 plus 100 ml plus 0.05 ml. This will be the total volume being referred to a reaction mixture, because I started off with 100 ml, and then when I add one drop, the volume will change. So how are you going to calculate the concentration of blue dye? If you know the mass of the blue dye, this is the molar mass. Look, molar mass is 792.84 grams or per mole. This is per carbonate, molar mass of per carbonate, or the blue dye, molar mass of the blue dye, sorry. Molar mass of the blue dye, not per carbonate. If I know the number of the mass, number of moles is given by mass over molar mass. You plug it in the molarity equation. This is 792.84. So you should be able to find the concentration of the blue dye. You can attach additional paper if you need. You can attach the additional paper if you need to show your calculation. At this point, you should be able to have the concentration molarity of the blue dye and the molarity of the peroxide. Peroxide, use M1V1, M2V2, all right? M1V1 equals to M2V2. For the blue dye, you use the mass of the blue dye and its molar mass to find the number of moles and the total volume in the reaction mixture. This will give you the molarity of your two reagents. Any question? Okay, no question, let's move on. Now, we will do the same thing we did before, all right? This is the molarity of the blue dye using 20 ml of the stock solution, calculated molarity of bicarbonate. This is the time. What a time for what? Set up a second, stop the timer when almost all the color faded. You can read this. So you need to know the initial value for the red color, so that what will be, I will do the calculation first, that what is the 90% of the initial before you added that. If and then you can record the time it takes for the initial color to fade to around 90%. You're gonna write it down there. You're gonna write it down there. All right. So that is what you need to do for the data sheet. Now, the concentration of, all right, right here, rate, calculated initial rate for part 2 rate will be given by the concentration of blue 1 dye over time. over time it takes to reduce to 90%. So the time you're gonna be using is here over the concentration of the blue dye. You know the blue dye. This is the same thing for round 2, except that you will increase the concentration of the peroxide to 40 ml. Set up a second run using higher concentration. In this case, you will prepare, all right? You'll prepare a solution of 60 ml of purified water and 40 ml of stock solution. This is for run 2. This is for run 2, which I know, look, you know the concentration of blue dye, you know the concentration of peroxide, using M1V1. You're gonna do that again. Remember for run 2, since you're using M1V1 for stock solution, what was the concentration of stock solution? What is the volume of the stock solution? So for peroxide here, for page 2 or to run 2, this is run number 2. If you recall, M1, I pick 0.2 hypothetically. V2 or V1, you are taking what? 40 ml, 40 ml. I'm just showing you how to complete this column, right? Or this on the table, this side on the table, the concentration for run 2. You use M1, V1 equals to M2, V2. You're looking for M2, V2, this is 100. Total volume when you add 60 and 40 is 100 ml. V2 is 100 ml, question mark. M1 is 0.2, the one I picked. You have to calculate for your case. V1 is 40. This is for run 2. This is for run 2. For run 1, you will do the same thing. So when you calculate molarity for hydroxide, peroxide, you'll end up with 2 values. Remember, in run 1, you use 20 ml. In run 2, you use 40 ml. So when you use M1V1 for peroxide, it will change. It will change. Bear in mind, it will change. But the concentration of, all right, the concentration of blue 1 dye will remain since you are using one drop all the time. And to get the calculated the rate, all right, you will use the concentration of the blue dye. Any question? You see here for 10, using the concentration of the blue dye calculated above and the time elapsed, you will have to calculate the rate, look at what I'm underlining. Calculate the rate of each of these reactions in molarity per second, which is right here. And if you look at my whiteboard, the whiteboard here is rate is given by the concentration of the blue dye for each over the time elapsed. That is how you complete the rate here. You know, if you don't make a connection, you will be in a crossroad or confused, like I have all this concentration. Which value am I going to use? And that take care of part 2. Any question on part 2, or we just dive to part 3? Any question on part 2? Any question on part 2? Look, any question? Nope. Oh, I was calling Angela and she's not here. Oh, I was just calling. I thought she came and maybe she left. That's fine. That's okay. Do you subtract 100 from M1? I don't understand what you mean by subtract. You don't subtract, you divide. I was saying this is, I was saying the R for this, sorry about that, you don't subtract. I meant to say that V2 is, the value for V2 is 100 ml. My stylus bamboo is kind of like messing me up. You don't subtract. I meant to say, let me just take this side, and I meant to say this. Look, I meant to say that V2 is 100 ml. Sorry about that. It looked like it was a subtraction. Any other question? Any other question? Good. Let's move on to 3. Part 3 is determination of activation energy, all right? The effect of temperature. This is where you will now have to prepare a water bath. So you shouldn't be, you know, far away from your kitchen, but instead of shuttling between kitchen and, you know, this is what I was thinking when I was reading this. I say, maybe I should recommend to you guys that if you have a thermos flask, you know, the flask or coffee cup, whatever, you can just prepare water in advance. Hot, you know, because you will carry out the experiment for part 3 at an elevated temperature, about 80. The solution should be 10 degrees higher than the room temperature, So that is what you need for part 3, water bath. Give you a heads up for that. You should have something like, you know, something which can hold, something you can immerse your clear, transparent cup in that water bath. It shouldn't be too small so you cannot have. The purpose is to warm the reaction. You want to warm the reaction, okay? Or carry the reaction at an elevated temperature. So in part 3, prepare a patch of water. All right, you can use a microwave and keep it somewhere. And like before, please do not use 250. Do not use this. It will not work. Remember to use the what? The transparent, not the 250 ml picker. And just like before, how are you going to measure the purified water? 80 ml, it is 50. Using graduated cylinder, 50 plus 30, that's 80. In here, measure out the stock solution again. So if you are started with 24 part 1 and 24 part 2, you should remain with 60. So you're now taking 6 out of 60, you're measuring out 20 ml of the percarbonate or OxyClean solution and add to your measured purified water. So 80 plus 20 gives you a total of what? Total volume of 100 ml, total volume of 100 ml. So this is what I was telling you, that you should have something large enough to accommodate or you immerse the water. You can place your reaction vessel. I'll recommend that, you know, the water path should completely, or the reaction mixture should be completely submerged in the water bath for about 5 minutes so that the temperature can rise to about 10 degrees more. So if, say, for example, the room temperature is 25, so my water bath should be able to raise the temperature of the reaction mixture to 35. From 25 to 35 is about, it shouldn't be precisely 10, it's around 10. If you have 12, if you have 15, that's fine, but not all the way like crazy, right? So once I bring the water to, or the OxyClean solution to a temperature higher than room temperature by 10 degrees Celsius, you will now prepare the reaction by placing the elevated temperature OxyClean solution on the red, and open up your what? Open up the calorimeter on your mobile or smartphone and record the what? You're gonna record the initial reading for R value. Snapshot, 3 times so that you find the average. Remember, this is now the R for part 3. This will be your R node is given by 1 plus 2 plus 3 values over 3. Take 3, 1, 2, 3, and then you divide. You're gonna write that somewhere as your R node. We're gonna use that to, as for your Planck, calculate for that. So that is what's gonna be your Planck node here. You will now get ready for data collection. Add 1 drop of blue food coloring, start the timer, and you're gonna record the value or snap the reading. So once you add 1 drop of blue dye, be ready with your smartphone every 30 seconds, 15 seconds. So you're gonna start, first of all, once you add the blue dye food, wait for 30 seconds. Once 30 seconds is over, you start 1, 2, 3. 1, 2, 3, 15 seconds. 1, 2, 3. 1, 2, 3. So that you'll have 3, you will later on process the raw data by picking the past 3, the past 3, the past 3, the past 3, 3, 3, 3 here, and then you find the average value. You find the average value of the 3 readings for each data point or for each time. You will calculate the observance on this side using the equation right here. Using the equation, observance equals to negative log of R for each time after 75, after 90, after 105, all of R initial. This is where you'll get the R node, all right? The first reading, the initial will be your denominator. The top part will be the values you will get from here. And to get the observance, which is A in this equation, observance, which is A in this equation, will be calculated using this A, all right, equals to negative log of R over R node. This is just a one stand. This is just a one value you'll get from the Planck. You will get from the Planck. With that, right, you have now the data, all right? You will have now the data to calculate the rate constant. What step number 12 here? What does step number 12 say? Prepare a straight test plot by the type that was determined in part 1. So, depending on which graph will test positive, let me just give you an example. If I had ln of A in part 1 was a straight line like that, all right? If it was a straight line, and then what I'll do is I'll plot the same graph for the part 3 data. So if ln of A, let's see, ln of A here, what does ln of A says? Ln of A, is it first order or is it second order? You can refer to the data sheet, I mean the background. ln of A on y-axis, look at my whiteboard. ln of A or observance on y-axis versus time give me a straight line which look like that. That means negative value for slope, you have to change it to positive equals to K. In other words, negative times negative slope like that should be the value for K. K is always positive. K is always positive. That is why you see a negative here and a negative here for this negative slope to make it positive. But you don't see negative in front because it's already positive. So negative times negative make it positive. This will be now what you will plot in part 3. In part 3, you will plot a graph which will test positive in part 1, okay? And get a value for rate for the rate constant. K is the rate constant. Remember, K is the rate constant. Prepare the straight line graph and determine the value for pseudo rate constant K. Pseudo rate constant. This is, let me just use this K like that, pseudo rate constant. You see this sum right here? Determine the value of pseudo rate constant for this reaction. What is pseudo rate constant? How are you going to determine that? Let me take a pause and ask you, how are you going to determine the pseudo rate constant? Anybody can take a guess? How are you going to determine from the graph? Or what are pseudo rate constant? Remember, I put an apostrophe up there. How will you end up with this one? From the Excel, let me just give you a hint. How are you going to determine that? You have to do the calculation or what? How are you going to get that? You know, sometimes when they ask you a question, they expect you that you already know what to do. For step 12 in part 3, how are you going to determine the rate or pseudo rate constant? Anybody want to try? Adam, you want to take a chance and see? Yes, thank you. Look, wouldn't you just find a slope? Yes, thank you. You use this trend line, you know, some use the trend, and I hope you know, you got to teach yourself how to find the equation of a straight line. M X plus P. Yes, you use equation of a straight line. We use equation of a straight line. That is what you need to do, of which this is the value for pseudo. And there are two values, by the way, there are two values of K. Remember, step number 12 here is talking about the pseudo rate constant. You're gonna have to go back again where we are going with that value. Once you have that, what I want you to look at is relate the pseudo rate constant with this. Look at this right here. There is, you see this right here? This is where we're going. So that when you see the bolded with an apostrophe, that is the value you will get from the graphs, two graphs for part 1 and part 3. And the equation of a straight line or the slope of your graph, the two graphs, are called the pseudo rate constant. It's not the rate constant. Look at what I've underlined on part 1. There is an apostrophe here, which is the pseudo rate constant. K here is the rate constant. There's a difference between those two. So we know, hold on. We're gonna come back to this equation. Fast forward to part 3, so you know where to find, how to find the pseudo. We are in part 3, step number 12, right here. prepare the straight graph and determine the values of the rate constant. Yes, from the two graphs. So I'll do for part 1 and part 2. So now you will, for part 3 here, you will calculate the observant, draw the straight line. Now the reaction mixture here, you'll find the concentration of the blue dye, the concentration for that for part 2 and 3, the initial for this, and average of the initial. This is before you start this is the final after the reaction. Part 3 here is the same thing, but the temperature will be initiated. Average temperature of the initial and the final, initial and the final. That means before the reaction and after the reaction. What is the average in degrees Celsius? And you know how to change what? To Kelvin. You add what? Add 273 K. Temperature in Kelvin is 273 plus the temperature in degrees Celsius. You can use 0.15, that's fine if you want to. This part 1 is at room temperature. This part 3 here is at an elevated temperature. Look at part 1 again. This is at room temperature. But here, this is at an elevated temperature. And then you'll find the reciprocal of the temperature in Kelvin. You'll find the temperature in Kelvin reciprocal 1/. Now, for data collection of part 3, for each of these temperature trials, that means room temperature and maybe 35, let me say 35, room temperature being 25, and another 5, that will be my T1. Let me just pick up as T1 equals to the room temperature, which is 25. I'm just picking up that, all right, plus 273.15. And T2 at an elevated temperature may be 35. Remember the direction said that it should be 10 degrees or more, plus 273.15. And then you're gonna find the reciprocal of that, of course. The reason why you have to find the reciprocal here is so that you plug it in the equation. This part 3 is determination of the activation energy. Activation energy. How are you going to find K1 and K2? For from the Arrhenius equation, let's see. K2, K1 equals to let me put here for the sake of rearranging the equation into 1 over T2 minus 1 over T1. You know T1 and T2, I just pick up from there. That is where my T1, T2, that is where you will gonna have for part 1 and part 3, whatever the temperature will go in there. You're gonna have this value for T1, let's see this, T1, that is given there. T2, you're gonna have that. What is the value for R? Anybody can give a guess on the value for R? What is the value for R? What's the value for R? What's the value for R? Yes, thank you, Mary. It is 8.314. This is joules per mole times Kelvin. This is the unit for R. Yes, it's gas constant, and Nicholas, there are 5 values with different units, and that's why I'm putting here units, whatever we are dealing with energy, you know. Yes, it is the gas constant, but gas constants have different values. Sometimes when we are working with pressure, you'll see 0.082 and then others. There are 5 values, but for our case, make sure you use this one. This is the value you're gonna use. You know, sometimes you may not see in the background, but I expect you that you are taking the course right now, or you're familiar, or you're covered, all right? Before we rearrange this equation to find the activation energy, how are you going to find the rate constant, not pseudo rate constant? Remember pseudo rate constant? Pseudo rate constant is what you will get from the slope. Somebody has said that. Remember from our slope right here? These are the abbreviated values, So the slope equation that were written next to the graph right here, right? This slope you are talking about, they are not rate constant, they are pseudo, and that is why here, look at the data sheet right here. Look at my Kawasaki. There is the K, which is apostrophe, and then there is the rate constant you have to calculate. The one you will get from the graph are pseudo, not the rate constant. I know it's, you know, in the lecture or in the literature, in the lecture, they might just say rate constant. They don't talk about the pseudo, no. So, and that is why in my whiteboard, I used the apostrophe to mean it is a pseudo. It is not the rate constant. So how are you going to calculate the rate constant? Look at my Kawasaki and let's all read. For each of the temperature troughs, that is 35 right here. Where is my 35? They are talking about the two temperatures. Say I just pick up 35 and 35, the two temperatures right here. Determine the value for the pseudo rate constant, that is the slope. Use the rate constant, that is the pseudo rate constant, and the what? And the concentration of the peroxide in the reaction mixture, previously determined for this reaction, to find the rate constant by using this equation. So this is from the slope. Look, this is from the slope. Look at the Kawasaki. This is from the slope. And reaction order, we determine the reaction order earlier on. All right, Nicholas, it crashed on you. Did I lose everyone? I see Nicholas, you are in. Yeah, Jacob is here. I see Nicholas. I don't see Nicholas. Are you in? Let me see. Somebody saying that I think Zoom just crashed on me. You have to go out and come back again, Nicholas. I see Nicholas. Nicholas, can you hear me? Can you hear me? Maybe it crashed.
Yeah, I can hear you. Just it cut out for me for a second. And the window closed for a second, and then it came back. It was weird.
So you can now, right?
Yeah, I'm here.
Can you see my screen right now?
Yep.
Okay, good.
Cool.
Good. Let me just mute you so that for background. So what I was saying here is the rate constant you got to calculate is from this equation one, the rate law, using the relationship. And remember, this is going to be for part 3 here. All right. You're gonna calculate the rate for K1. K1 is for temperature 1. This is, let me call this room what? Room temperature equals to K1. And then this one is elevated what? Elevated temperature, which is equals to K2. Where we are going with this K1 and K2, let me just get this snap room right here. Where we are going with K1, K2 here is the Arrhenius equation here. Remember, the objective for part 3 is to find the activation energy right here, activation energy. There is no way we can rearrange this equation here unless we know K1 and K2, unless we know K1 and K2. And K1 and K2, it is not from the graph. We have to calculate using the pseudo. Pseudo is now for the graph, of which I can say here for K1, K1, that is at room temperature, will be given by the pseudo for the graph. This is from the graph over the concentration of the peroxide. All right, you should have this value somewhere, over the reaction order with respect to peroxide. This is room temperature. And then at the elevated temperature, all right, K2, like that, is given by, at the elevated temperature, that is the pseudo from the graph, over what? Over the concentration of the peroxide, all right, raised to, all right, raised to the reaction order with respect to its reaction order. That will give you K2. And then we can now rearrange this equation right here, to get the activation energy, Before even I do that, that is how now the difference between this is from the graph. Look at my cursor key here. This is from the graph. This is from the graph. K1 and K2, this is for my K2 at elevated temperature. This is the K2, and this is from the graph. Right here is the graph, all right? Now, K1 and K2, once you get the values for K1 and K2, activation energy now, EA is given by, if I take negative R, that means I'll take the negative at the top for activation energy and let it go on the other side. On the left side of the multiplication sign, it will be multiplied by ln of what? Ln of K2 over K1, all right? Ln of K2 over K1, this is K2 right here, over what? Over 1 over T2 minus 1 over T1. And this will give you the activation energy, this is the setup. I need to see the calculation, all right? Remember to include calculation. Attach your calculation. I wouldn't mind if you say below is the calculation, or when you put the value here, I know you don't have space to do all these kind of calculation. You don't have space to rearrange this equation to get the rate constant. Use any additional papers to the calculation, show the calculation. The rate law here, remember you did exact same reaction at room temperature and at elevated temperature. Which one are you going to use to write the rate law? Rate law, use only the rate constant for the room temperature. That means we are going to use the this one for the room temperature right there. That means you're going to use the rate constant for at room temperature, that is K1, to write the rate law. Of which rate law in this case is what we started with. All right, rate law will be now K1, which is at room temperature. This is K1. It is not K1 prime. It is K1 at room temperature times what? Times the concentration of the blue one dye raised to the coefficient, or raised to its reaction order, times the concentration of the peroxide raised to what? Raised to M, which is the reaction order with respect to the peroxide. Oh, you don't see the M right there? Yes, that is what I meant to show you on my whiteboard, on how you're gonna write this right here. And that is it. You know, that marks the end of, you know, the post-lab here. Don't attach to this question here, please. Just how I have been making or streamlining the pre-lab and the post-lab is just go to the assignment and click the post-lab number 4 or pre-lab number 4. You know, don't worry about, you know, answering the post-lab here and attaching it to the data sheet. The data sheet will just be submitted via the data sheet folder. The pre-lab will be submitted via the pre-lab folder, and the post-lab will go with the post-lab folder on Canvas. With that, that marks the end of our pre-lab lecture today. I am glad you are able to tune in today, because somebody who didn't turn in or didn't tune in for Zoom session, and probably maybe they just dive. They just say, hey, I know what is going on. Let me get started with the lab. You know, I know what I'm doing. I'm gonna use the 250 ml beaker. It's not gonna work. You know, the values will just, because the beaker they talked about in there is not transparent. It's much later on when we receive all this, we thought they were gonna mail in a clear, transparent beaker, similar to what we have in the lab, but it is just plastic, which is not transparent. So whoever is not here, they did that, they will get back with me and say, it's not working, what happened? But if they go back and watch the pre-lab lecture recording, which I intend to share in a few minutes, and then they should be able to proceed with the lab experiment and do the calculation. With that, if there is no question, the lecture is over. I would like to end it here unless there is any other question. You are free to leave. Thank you. Thank you, and thank you for tuning in. Please stay healthy. See you next week, same time. If you have any question, you can send me an email. I'm always staying on my, you know, unless I'm on the road or sleeping, I stay online most of the time. Send me an email and I can request Zoom session that you have time. Can you come on Zoom session, and then we can work one-on-one on the calculation. See you next time. I'm gonna stop sharing my screen right now and end the session. Thank you. I'll see you next week.